Welcome to week one of programming and problem solving. Week one's topic is data analytics. A high level overview of this would include three major points. What is data analytics? The history of data analytics, and then newest topics of big data and the Internet of Things, which is denoted by IoT. Data analytics refers to a qualitative and quantitative techniques and processes used to enhance productivity and business gain. You extract your data, you're going to categorize it to identify and analyze behavioral data, patterns, techniques, sequences, if you will, varying along organizational requirements. Sometimes you're going to see a lot of different similarities in words that are used, one of which is data analytics is also known as data analysis. Could be called a lot of different things. Data analytics, it's primarily used to conduct business to consumer applications. There's lots of applications in global organizations because everyone is going to collect data. They're going to analyze the data. They're going to use it for marketing economics and so forth. So evolving data facilitates through decision making. For example, social networking website is going to collect data used based on user preference, community interests, segments, and so forth for specified criteria, and they're going to use this to determine what is the optimum output that can be achieved based on how they will focus and edit their website. So the history of data analytics, you'll see a lot of similarities in this because there's huge overlaps with this. But data analytics has a lot of different names. You will hear this called data science, statistical analysis, management science, which includes operations research, decision science, and so forth. Management sciences and decision support, what differentiates these areas is primarily the type of quantitative tools and methods that you're going to use to solve these problems. For example, if you have a goal to predict a variable and variation exists between the data, then you're probably going to use some sort of statistical model. If your goal is to seek optimization given resource constraints, well, then you're probably going to use something like operations research from management science. Operations research is probably a very, very widely used application of management science. It kind of got its start around World War II over in England. Common problems with this that you would use operations research models for includes inventory problems, allocation problems, queuing models, which are also called waiting lines, sequencing problems, how should you change the workflow so that you can achieve optimization, routing problems, typically these are called the traveling salesman problems, replacement problems, competition, search problems, and so forth. So management science, it's a very broad interdisciplinary study of problem solving and decision making in human organizations. It has very strong links to economics, business, engineering, and many other sciences. It uses various science research-based principles, strategies, and analytic models, including mathematical modeling, statistics, numerical algorithms to improve an organization's ability to enact rationally and meaningfully management decisions. The field originally started as applied mathematics, where there were early challenges where problems related to optimization of systems could be modeled after a linear model. For example, you wish to achieve the optimum maximum profit, minimum cost, maximum throughput, and so forth. Another very large area is statistics. In statistics, it's generally divided into three categories: descriptive statistics, inferential statistics, and statistical modeling. If you take a stats course, you're also going to talk about probability because the probability is there needed to perform other aspects of the inferential statistics. So descriptive statistics deals with the presentation and the collection of data. Usually this is what you would conduct as your first part of a statistical analysis. It's not as simple as it sounds, though. A statistician needs to be aware of designing the experiments, choosing the right focus group, avoiding biases. All of those can cause problems if they're not properly done. Different areas of the study requires different kinds of tools. For example, physicists may use studying turbulence in a laboratory needs the average quantities that vary over small intervals of time. The nature of this problem requires the physical quantities to be averaged from a host of data collected through the experiment. Inferential statistics, as the name suggests, involves drawing conclusions from statistical analysis that can be performed using descriptive statistics and the probability. In the end, the inferences that studies make here are important, and this aspect is dealt with in inferential statistics. Most predictions and future generalizations about a population, they're done by studying a smaller sample that comes under the the wings umbrella of inferential statistics. For example, a lot of social science experiments deal with studying a small group of population that helps them determine how the population behaves in general. By designing the right experiment, the researcher is able to draw conclusions relevant to the study. So one thing that needs to be very careful is not to draw the wrong or biased conclusions. Even though this appears, in science, there are ways in which one can manipulate studies and results from various means. We're going to talk about, in the last week of the class, about reproducible research, which is really very, very important. So we'll talk about that again later. One example that is growing in being problematic is computers hold lots of information, and it's easy, either intentionally or unintentionally, to use the wrong inferential methods. So the problem with inferential statistics that is typically solved or used here is targeting, called hypothesis testing. Sometimes it's called A/B testing. It's a very popular application of this. So a statistical hypothesis, it's an assumption about a population parameter. The assumption may or may not be true. You have to test it. So hypothesis testing refers to the formal procedures that you're going to use to accept or reject these hypotheses. So the best way to determine whether a hypothesis is true is to examine the entire population. That's often impractical and not possible, so they will take a random sample of the population, and then that is used to conduct the hypotheses. There are two hypotheses, one of which is called the null hypothesis. Typically, this is denoted by H sub 0, and it is the hypothesis that results purely from chance, or currently what you're experiencing as a present method of operation. The alternative hypothesis, sometimes called the research hypothesis, is what you hope to prove. So here's an example where you may have an experiment where you're trying to determine if a coin is fair and balanced. So a null hypothesis would be that the flips would result in heads and half in tails, half in heads and half in tails. The alternate would say that the number of heads and tails would be very different. You may think that the coin's loaded. So the formal statement of the hypothesis looks something like this. You flip the coin about 50 times, 40 of them results in a heads and tails. Given this, you would probably be inclined to reject this, to say no, the coin is biased. Statistical modeling is probably one of the two top modeling techniques that will be used in management decision making. It's a class of mathematical models which is based on assumptions concerning the generation of some of the data, similar data from a larger population. The model represents, and it's often in ideal form, the data generating process. The assumptions contained in this describe a set of probability distributions, some of which are assumed to adequately approximate the distribution from which the data was sampled. So what happens with this is that a statistical model is going to be built to determine prediction. You might use it for prediction and so forth. One thing that's really important is that to understand that the model is not reality. It's just a formal representation of a theory, but it's definitely not reality. So another area that became really popular in, I guess it was about the 90s, is this area of business intelligence. And business intelligence is a set of techniques and tools that acquires data and transforms the raw data into meaningful and useful information for business analysis purposes. And I will also say that the graphical capability of this, the presentation, graphical presentation of the data, is extremely important. So you'll see the term data surfacing. It's also used with BI functionality. This is capable of handling large amounts of data. They're going to grab data from multiple sources, and the goal here is to take this data and create it in a format, put the data in a format that's going to be very easy to interpret these large volumes of data. You may see something like dashboards, corporate dashboards. This is an example of business intelligence. So some of the features, common functions of this would be reporting, online analytic processing, analytics, maybe data mining, process mining, business performance management, benchmarking, predictive analytics, and so forth. It can be used in a wide range of business decision making, from operations to strategic. If you see companies that are using dashboards, this is a perfect example of this. It combines external and maybe internal data that provide a more complete picture, and then creates this intelligence for the business applications. So along with these tools, they empower organizations to gain insights into new markets, assess demand, suitability of products, gauge the impact of marketing efforts. And there's a lot of different things, categories that are listed under business intelligence. So everybody, I'm sure in class, everyone has used a spreadsheet. If you've used a spreadsheet, you can say that you have been involved in this area of excuse me, of business intelligence. OLAP, online analytical processing, if you have drill down capabilities and stuff, data mining, data warehousing, and so forth. All of these are very, very popular tools in terms of this. So a new term that kind of came out, I guess, within the last couple of years, and it was coined by a company called Alteryx, which is a very powerful tool for you. It's data blending and analytic tool, but they call it a data artisan. So a data artisan is someone who uses data analytic tools to create analytic applications that are used to avoid pitfalls in people that aren't quite so well versed in the analytics, to build these tools, and it allows them to create value very quickly. One of the big areas of this is called data blending, which means that you bring data from a lot of different sources together. You're going to combine the data into one analytic data set, conduct the analytics on that data, and hopefully you're going to bring forth some new and actionable insights. This involves the graphics of this as well. Now we're getting to the, I've heard this called the sexiest job description or job title of the 21st century. And I have to chuckle at this because when you hear the word data scientist, and this is one definition, and I found that data scientist is a person who has the knowledge and skills to conduct sophisticated and systematic analysis of data. They extract insights from the data sets to produce development, for product development, for example, and evaluate and identify strategic opportunities, bring forth new insights, and so forth. I'm not going to read through all of these, but this article that I found had all these different definitions of a data scientist. Data scientist is that unique blend of skills that can both unlock the insights of data and tell a fantastic story about the data. That's one of the things that I'm going to bring forth on this a lot, is the storytelling aspect of this, because data scientists, these skills have been together in various shapes and forms and people for a long time. Now they're pulling this together, and you will have people who can gather this data. You have people that can analyze the data. You can have people that can tell the story of the data. Data scientist does all of this. And here's a graphic that I like to use a great deal on this. A data scientist, he's a data processor, he's a visualizer, he's an innovator, he's a data miner, researcher and analyzer and data conditioning. All those together come together as a data scientist. But the one that I want to add to this is storytelling. Data visualization expert Stephen Few, and his name is very, very popular in this right now. Numbers have an important story to tell. They rely on you, the data scientist, to give them a clean and convincing voice. If you can't tell the story about what the data is telling you, you're not going to have the same kind of impact before. And it's not going to be as meaningful. So data storytelling, it's a structured approach for communicating data insights. It involves combination of these elements, data, visualizations, and the narrative. It's important to understand how these different areas combine, these elements combine together. But the whole purpose here is that you're going to bring all this data together and you're going to analyze it. And then once you've analyzed it, and keeping in mind the business need, what's the business objective, you have to convince your user community that here's what the most important output from the data is. You have to tell that story. And the use of graphics is extremely important for this. So I've left some links here that you can go and check out to read more about this. I also got this recently about 8 data skills to get you hired. This is a core set of 8 data science competencies that you should develop. One of which is basic tools. You have to have a really good understanding and knowledge, skills on using basic analytic tools. There's a lot of them out there. There is this package called R, which is falls into the free software domain. And then there's Python. I know a lot of people use Python to read data from different sources. And also a database query language like SQL is extremely important. There's other tools out there. I think I mentioned down here later on. But there's other tools like Alteryx that I mentioned earlier, and also SAS. You have to have a good understanding of basic statistics. This is, an interviewer once told me that many people he interviewed couldn't provide the correct definition of a p-value. You should be, that's the probability value from a hypothesis test. You should be very familiar with statistical tests, distribution, things like maximum likelihood estimators and so forth. Think back to your stats class. I was interviewing a candidate several years ago, and he was supposed to have a bachelor's in statistics and top of his class and so forth. I asked him some very basic questions, and he couldn't answer them. Well, obviously, he didn't get the job. So there's a new technique called machine learning that's very powerful. People use that for classification and different techniques and so forth. So when different techniques give you a valid approach, that's what you should use. It's important at all company types, especially data-driven companies where the product is not data-focused. Product stakeholders will depend on you to help make decisions and so forth. The article listed machine learning. I added advanced modeling. If you're at a large company with a lot of data, working at the company, you need to be, if it's data-driven, then you need to understand these statistical techniques. Machine learning is a method of classification. There's other ones called, like cluster analysis, random forest trees, all of these machine learning buzzwords. It's true that there's a lot of techniques that can be implemented using R, which is free, or Python, but it's not necessarily a deal breaker, but you need to know how to use some of these tools. Most importantly is to understand, at a very high level, what really is appropriate in tools to use. It does help to have a really good understanding of multivariate calculus and linear algebra. You may in fact have to derive some of these particular algorithms yourself. And unless you have this background, it's going to be hard. You may wonder why a data scientist would need to understand this stuff. If there's a bunch of out-of-the-box implementations, already out there. The answer is at a certain point, you might have to punt. You might have to come up with your own particular application. The article called this data mugging. I called it blending. So munging, blending. That is, you're going to have data that's going to be messy. It's going to be in flat files. It's going to be in structured databases. Could be in unstructured databases. Comes from a lot of different places, and you've got to take this dirty data. You've got to transform it into clean data so that you can analyze it. Here's an example. Some of the examples here includes missing values, inconsistent strings, and so forth. You might have a string that includes the word New York with capital letters. Instead, it might have New York with lowercase, which is different value than this, or it could just have NY. So these are things that you really have to work on. Your data blending skills will help you with this. A tool that I use quite often is called Alteryx, and Alteryx is a very powerful tool. It's very robust. You can use it for a lot of applications. Now that you have your data into the data set and you built models, you have to communicate the results. And this falls under the data visualization and communication. Visualizing and communicating the data, it's extremely important, especially at young companies who are making data-driven decisions for the first time, where data scientists are viewed as people who help others make these decisions. When it comes to communicating, this means that you're going to describe your findings and the way the techniques that audience will understand, both technical and non-technical. There's a lot of different visualization libraries out there, one of which that I've got some experience in the R package. There's a thing called ggplot. There's also some free graphic tools called d3.js. So you can go to www.d3.js and it shows you tons of these. And these are free. Another area is the software engineering, because if you're interviewing at a smaller company and are one of the first data science hires, you're going to have to make sure that you have a very strong software engineering background so that you can get the data. You're going to be responsible for handling a lot of data logging and potential developing these data sets. I found this also a great way to describe this is called the analytics in context. Where you're going to design something, you'll have the data management, you conduct analytics, you validate it, you visualize it and integrate it, and then it continues. So one of the big topics that you hear a lot of people talking about now is this thing called big data and also the Internet of Things. Big data is always going to be bigger. So it's a term used for data sets that are so large or complex that traditional data processing applications are inadequate. If you can't read it in, you can't analyze it. So some of the challenges includes the analysis, capture, data curation, the blending of this, search, sharing, storage, transfer, visualization, all because of the mass volumes of data. It often refers to the use of predictive analytics, behavioral analytics, and certain other advanced data analytics methods that extract value from the data. And it's seldom to a particular size of a data set. When it comes to this, it's talking about just the volume. So the size is irrelevant here. Accuracy in big data may lead to more confident decisions, and the better the decisions can result in greater operational efficiency, cost reduction, and reduction of risk. Analysis of data sets often lead to correlations to spot business trends, prevent diseases, combat crime, and so forth. Scientists, business executives, practitioners of medicine, advertising, governments, all alike regularly meet difficulties with large data in areas including internet searches, finance, business informatics, and so forth. Scientists encounter limitations in certain areas like meteorology, genomics, complex physics simulations, and so forth. Excuse me. These data sets are growing rapidly. Because of the amounts of data that they are increasing. And also with the cost of storage dropping, this is growing at an exponential rate. So these data sets, big data collecting radio frequency readers. I read an article not too long ago about a major shoe store that was having a lot of issues taking inventory. They put RFID chips in the boxes for the shoes so that when the shoes left, it adjusted their inventory. Pretty cool. So, relational database management systems and desktop statistics visualization packages, they often have difficulty handling big data. So you have to have the right hardware and software that can be used to conduct this. Complexity of the data comes into play. This kind of goes back with the data gathering and cleansing. Data can be structured like in a database, like an Oracle database or DB2 database, or it can be structured like in a text file. Text files are becoming very important and very, very popular because they don't take a lot of room, but you can store lots and lots of data. But getting the data out of there and getting the right data can be problematic. So here's where I mentioned some of these other tools: SAS, Alteryx, Python, SPSS. All of those are more sophisticated analytical tools that should be considered. And then you hear about the Internet of Things, refers to an ever-growing network of physical objects that feature an IP address for Internet connectivity and the communications that occurs between these objects and other Internet-enabled devices and systems. This extends Internet connectivity. IoT extends this beyond traditional devices like desktops and laptops, smartphones, tablets, to a whole diverse range of devices and everyday things that utilize embedded technology to communicate and interact with the external environment and the internet. So anytime that you see those cameras out on the street on top of telephone poles and stuff, this is what they're talking about. So here's some examples. It could include security systems, thermostats, cars, electronic appliances, lights in the homes, alarm clocks, speaker systems, vendor systems, and so forth. Business can leverage these applications to automate safety tests. For example, notify authorities when a fire extinguisher in a building is blocked. It can perform real-world A/B testing, like hypothesis testing, using network cameras and sensors to detect how customers engage with product. Now, the future of IoT is really pretty much open to discussion. There's more than 12 billion devices that currently connect to the internet, and researchers believe that by 2020 there will be 26 times more things connected to than people. According to Gartner, consumer applications will drive the number of connected things, while enterprise will account for most of the revenue. IoT adoption is growing with manufacturing and utilities. They're growing exponentially. So what is this Internet of Things? What does it matter? It isn't new. Tech companies have been doing this for decades. The first internet-connected toaster was unveiled in 1989. That was even, before the internet really became really popular with this. At its core, it's very simple. It's connecting devices over the internet, lets them talk to us, the applications. If silly example is a small fridge, what if your fridge could tell you that you're out of milk? Texting you the internal cameras saw that none was left, or that the carton was past its use-by date. While it's not most common, in Britain at least, in some home and energy systems, partially because the government is pushing energy companies to roll out smart meters. They have clever functions that let you turn on the heat remotely, turn the temperature up, turn it down, and so forth. So some of you may even have smart homes where you have your appliances connected. I've got my thermostat connected to a smart home application. I can check the temperature while I'm gone. I can turn it up. I can turn it down. Monitor this. If it gets too hot in the house, it'll send me a text message. I've got my garage door opener hooked up to a smart home application so that I can open the door, shut the door from anywhere that I have an internet connection. So, what does this matter? There's a reason the government is encouraging energy companies to hand you a smart meter. All the data is automated, it's more efficient, meaning that we use less energy. Many areas of this show benefits, though through some smart gadgets are more about whiz-bang effects than efficiency. So, is it safe? Two different schools of thought on that. Can Internet of Things be secured? Anything new and shiny has its downside. Security and privacy is a big challenge. If somebody can hack into my home network, they can open up my garage door, they get access to my garage and all the things in the garage, that could be a problem. So if it's shared with other devices and held in databases by company, yeah, there's an issue that could happen. Security experts argue it's not enough currently being done to build security and privacy into IoT at these early stages. So they connect baby monitors to automated lighting, smart fridges, as well as citywide systems, traffic signals, and so forth. Hackers haven't, for the most part, paid too much attention to this. There are likely not enough people using connected appliances for an attack, but the more that grows, it could be. So the short answer is yes, it's relatively safe. You're not likely to face serious loss or damage because of your smart device any more than your home PC. So there's no guarantee as far as not enough being done to ensure this, but how will this affect our business and work? It depends on your industry. Manufacturing is probably the furthest ahead in IoT because of the many different steps in a manufacturing process. Farmers have been using connected sensors to monitors for both crops and cattle in the hope of boosting production, efficiency, and tracking the health of the herd. The examples are endless, and all we can predict is that connected devices will likely creep into more businesses, and I'd say in homes, just the way that computers and the web has. When the efficiencies with the tools or plants, it's easy to appreciate the potential benefit, but when it's office workers who are being squeezed into more productivity, it could take a bit outside of this. So imagine your security access card being used to track where you are in the building, so your boss can, determine how much time you're spending in the kitchen area, making tea and so forth. On the flip side, a smart tea maker knows just when you're in the need of a couple that would be very handy. So, what does the Internet of Things mean for healthcare? Smart pills are connecting to monitoring patches, highlighting the life-saving potential. Many people are already strapping smartwatches and fitness bands to their wrists so they can track their steps and heartbeats on a run. There's a lot of clever connected healthcare ideas. Bands that track how much patients with a Parkinson's shake. Collecting more accurate data that's with paper and pen. Daily activities of seniors or ill people to watch for anomalies. People with heart disease and so forth. Healthcare is one area where more data has the potential to save lives by preventing disease, monitoring it, analyzing it to create new treatments. However, healthcare is also the most sensitive areas because of privacy and security. Is it real? Yeah, it is real. This is perhaps the best query being Googled about IoT. Is it real? Surprisingly, it's tough to answer. The technology is full of marketing and hype. It's often difficult to decide whether you have an innovation that's truly groundbreaking or not. After all, many tech folks are mocked by the first iPhone, but we've got millions of them. The Internet of Things is one of those wider ideas that isn't dependent on a single project or product. Smart fridges may be the appliance of this future, but could fall by the wayside as too much tech for too little gain. But the idea of connecting sensors and smart devices make decisions without your input continue. A decade from now, everything could be connected, or perhaps only in bits and pieces with specific benefits, such as smart meters. So it's really kind of hard to tell. No matter where it is and what you call it, it's real. What it will look like in the future is something that Google can't even answer. If you ever saw the TV series Person of Interest, you ought to watch it sometime because the whole series is based on IoT technology. Of course, it's got a bit of a sci-fi twist, but that is a really good example of that. That concludes the lecture for week 1 on data analytics.